Let's do this. All right. So we will do the introduction. All right. Today it is my pleasure to introduce our speaker, Justin Strauss. Justin is an associate professor in the Department of Earth Science at Dartmouth College. He received his BA in geology from Colorado College before earning both his master's and his PhD from Harvard. Justin's research sits at the intersection of stratigraphy, geochemistry, and paleontology with a particular focus on the Neoproterozoic Paleozoic successions. Much of his work centers on high latitude regions. Today, he will be speaking with us about the Ediacaran Cambrian transition in northwestern Canada. Please join me in welcoming Justin Strauss. Justin, the floor is yours.
Awesome. Thanks, James. Appreciate it. I'm just going to hide these meeting controls for a sec. All right. Yeah, it's a pleasure to be here. What I thought I'd do today is just kind of walk through work we've been doing in Northwest Canada for a bit over a decade now on this time interval. You're looking at an image here of the Wernecke Mountains. And I thought, given the composition of these seminars and folks that come, I try to break it up into kind of three geo-vignettes, as kind of Tony Prey would call them, that tackle slightly different problems but might have broader interest to different groups of folks that are joining. So it probably doesn't take much to motivate. Let me start that. Yeah, to motivate this problem amongst the composition of the group. We're going to focus in on the Ediacaran Cambrian transition, and I'm just using a kind of compilation figure from one of Fred Bowyer's recent papers that look at, the isotopic volatility in carbon isotopes through this time interval, the appearance of different types and turnover different types of organisms, including the Cambrian radiation. And so, yes, we know there's a lot going on here. I don't need to spend that much time kind of digging into this background. But what I thought I'd do is just kind of review what my group's really been interested in a kind of bigger scale. So one question we've always been interested in is, how can we better constrain how time is distributed in the Ediacaran, but particularly in Precambrian basins more broadly. We're limited to, kind of handfuls of age constraints and a lot of successions. What are the causes and consequences of some of the carbon isotope volatility, including other isotopes, but in this case, we're looking at carbon isotopes across this time period? Obviously, you can see there's a lot of variation, as many of us are familiar with. And then also, a third set of questions is particularly related to the Ediacaran period. What's the relationship between environmental change and this kind of story of biological innovation and turnover across this time interval? So these have been some, big scale motivating questions. They're large scale, right? There's no way I can talk about kind of in any one of these in enough detail in this kind of 50-minute seminar. So what I thought I'd do is kind of take those questions and look at sub-questions within them today. So these are kind of our geo-vignettes. And so the first question we're going to look at is, can we use our understanding of subsidence in sedimentary basins to aid in how we create Precambrian age models? Second question is, what's the stratigraphic expression of the Shuram carbon isotope excursion in northwestern Canada? So a little bit more focused, but we'll tie in other successions. And then the third question is going to be, what are the kind of this current state of our understanding of evolutionary patterns in the Ediacara Biota of northwestern Canada? And so the big question, I think, to frame right off the bat is going to be related to why are we working up here? So we're going to mostly focus today on kind of the boundary between Yukon and Northwest Territories and the Mackenzie and Wernecke Mountains. I'll introduce that a bit later. But there have been a lot of folks involved in this work over the years. This is just a list of folks I've been working with a bit more recently. Lots of different funding agencies, but the most recent work I'll talk about today has been funded by this 5-year FRES project looking at the Ediacaran Cambrian transition that's involved the kind of PIs here that are highlighted in blue. But a lot of the other work I'll be talking about today includes work with Scott Evans at the American Natural History Museum and Eric Sperling and Tom Bogue at Stanford, as well as a suite of Dartmouth PhD students over the years, Raina Harding, Tianran Zhang, and James Bush. So I'm going to be kind of going through a lot of different stuff, different projects, but I want to make sure I highlight a lot of the different folks that have been involved in the work. Okay, so why northwestern Canada? Well, you can see in this photograph in the background, if you land in the right spot in the Mackenzie or Wernecke Mountains, in this case, you could go to a location where you put a camp here, and you could be camping on the Marinoan cap carbonate, which is this bright white layer here. And on one ridge system, it's a lot of hiking, but you can slowly work your way up the ridges to the base of the Cambrian along one succession. And so the exposure, as you can see, is pretty spectacular of this time interval. The rocks are low metamorphic grade. There's really good preservation of primary sedimentary fabrics. They're fossiliferous, as we'll talk about later, and they have proven potential for geochronology, particularly rhenium osmium-based geochronology. There's an established baseline for various geochemical proxies, including both redox and kind of standard stable isotope-based geochemical proxies. And the part that interests me the most, and I think is perhaps why northwestern Canada might have one of the most important most important contributions to this time interval is you can see and we can reconstruct shelf to slope transects across somewhat isochronous successions. So that ends up being pretty powerful, as we'll talk about today. And then the other thing is we have some really well-developed collaborations with various First Nation communities. So we can actually connect with folks in the communities and do a lot more to kind of expand the scope of our work locally. Okay, so just a little bit of context for why we work in this part of the world. The other reason is when you look at a map distribution of rocks of this age, they're really, really widespread. So most of you folks will be familiar. This is an outcrop pattern of, so the Windermere supergroup, this would be basically, depending on who you talk to, basically late Tonian or Cryogenian up into the early Paleozoic. In black, that's the map pattern distribution. You have in gray the Paleozoic kind of myogeoclinal rocks shown in light gray. And as you can see, there's a lot of these rocks exposed up here, the boundary between Alaska, Yukon, and Northwest Territories, as well as through BC. So if you zoom in now on a map, geological map of that region, this is the outcrop distribution of various units of interest. Today, we're really going to be focused in on this kind of dark blue unit of the Hay Creek, Rackla, and Coates Lake groups. And you can see the outcrop distribution is pretty extensive. So it extends about 700, maybe 800 kilometers across strike from the southern Mackenzie Mountains, which is kind of this region, into the Wernecke Mountains, which is this region, and over into the Ogilvie Mountains in this part of the world. We're primarily going to be focused in on the Ediacaran Rackla group today, and that includes the basal Raven's Throat Formation, which is the Maranoan cap carbonate, up into the Sheepbed, Nataline, Game Trail, Blue Flower, and Risky formations. The Game Trail formation we'll talk about records the Shuram carbon isotope excursion, which I'll talk about later. So I'll mention a little bit of the older rocks, but this is really going to be our focus for the day. Okay, now one reason I mentioned that this ends up being a really important part of the world is that you can go from platformal to basinal rocks. And so this is a very schematic breakdown, but rocks to the east and north in the Ogilvies and east in the Mackenzies record shallow water sedimentation, platformal sedimentation. And then there's a distinct kind of transitional zone, and you go off to the southwest into basinal rocks. The names here, the Selwyn Basin, the Mackenzie Ogilvie platforms get used quite a lot, but they're really kind of a Paleozoic feature. But this is still the Cordilleran fold thrust belt, right? So all of these rocks are imbricated. So you got to pull back the deformation. You got to do some really detailed mapping to kind of deal with the complexities locally to then reconstruct kind of these shelf slope transects. But the nice part is they're telescoped, and so you can go from one camp on the shelf out into the slope and be able to kind of reconstruct things in that three-dimensional paleo-bathymetric framework. Okay, so let's jump into this first question. This is going to kind of divert a little bit from northwestern Canada, but I think it's important and useful for kind of this group to kind of be aware of some different ways of thinking about age models. Okay, so a simple question would be, let's say we've got an age based on correlation of the Maranoan cap carbonate at 635, and we know the Cambrian's up here. How do we know how time is distributed in this giant succession of rocks? Let's say this is about 2 kilometers thick, right? And especially if we lack any radiometric age constraints, or if we lack fossils to try to help us from a relative age perspective. The answer is we don't really have a great sense, right? You might say, well, I know the old constraint down here, I know the young constraint down here, and I'm just going to assume that there's somewhat linear sedimentation rates over time, and therefore I can just roughly get a sense of how time is distributed based on that. And a lot of the kind of classic age models we've used have done this, right? Between 2 points, we have radiometric age constraints. Let's assume a linear sedimentation rate connecting those, and we'll just kind of link it together. in that kind of framework. But as all of us know, right, looking at sedimentary basins, like time is variably distributed, right? You might have faster accumulation rates in the beginning of the section that then slow down over time. You might have moderate accumulation rates and then a large disconformity or times missing, right? And then the onset of accumulation rates again. Obviously, there's a lot of variability, right? So what additional tools are available to address this when we lack abundant radiometric or relative age constraints like we have in the Phanerozoic, right? What could we use to our knowledge, right, to help us, especially if we only got a handful of constraints? Well, one thing you could think about is how subsidence is generally distributed in different types of sedimentary basins, right? So for instance, if you look at kind of rift-related passive margins, right, generally accumulation rates are pretty fast in the syn rift phase and then slowly decline exponentially in kind of the thermal subsidence phase of the basin development. It's kind of different from foreland basins that generally start a little bit slower in accumulations and rates and then have an increase in sedimentation rates to function with flexure. And then, strike slip basins tend to be much more complex, but the basin generally just the bottom kind of drops out. So we can use this information to our benefit to help us understand, if we are in a succession that's rift related, perhaps we should be able to think about time distribution more connected to kind of understanding a syn rift versus a thermal subsidence phase, and maybe thinking about how that could affect our understanding of how time's distributed between two different relative or radiometric age constraints. So how are we going to do this? Well, the way we've been thinking about this is going back to some classic papers, right? So this is simplifying a rift-related kind of thermal subsidence modeling by Mackenzie in 1978, right? Which is just through one-dimensional uniform instantaneous stretching and subsidence, right? So you start on the left with kind of a very simplified unstretched crust type scenario, asthenosphere and mantle lithosphere above it, right? At stage one, you generate uniform and instantaneous stretching, right? That creates subsidence, right? Which then creates a basin above that. That amount of stretching is governed by a term that we call the beta factor, which is just the extended width over the initial width. As you thin the crust, you get upwelling of the asthenosphere, heats the lithosphere, right? And over time, that lithosphere cools and contracts and subsides as a function of that contraction at a rate that's proportional to that spreading or that stretching, right? And so you add a little bit more subsidence in that thermal kind of contraction phase that in this case we'll call rift-related thermal subsidence, right? It's just an isostatic adjustment. It's a highly simplified model. There are more complex rift models out there that we could use, but as a starting point, this is worthwhile to consider. Okay. Now, if you connect that now to thinking about tectonic subsidence, that's what we're talking about, right? Which is a function of that syn rift phase and the thermal subsidence phase. Over time, in a rift-related succession, you would expect faster accumulation rates in the syn rift phase, followed by the onset of that thermal contraction phase that has this exponential decay relationship, right? The amount of tectonic subsidence should be a function of the beta factor, just how much you stretch the crust, right? Larger beta factors, you get more stretching, and therefore you have more accumulation, greater tectonic subsidence. Sure enough, when you look at like passive margins around the world, right? A lot of these passive margins, or all of them, follow the same general pattern, right? A steeper syn rift phase and then a phase of thermal subsidence afterwards, right? So the point of this is that in rift-related basins, which are many of the basins that we study in the Precambrian, and this also applies to like interctonic sag basins, right? We can use our understanding of subsidence patterns and the attendant accumulation rates to better inform the age models, right? We don't necessarily always have to use a single assumed linear sedimentation rate. We could think about how that sedimentation rate should decline over time as a function of where you are with respect to the rift to drift transition. Okay, so how would you do this, right? So tectonic subsidence, right? The first thing you have to really think about is that's actually the total subsidence we see minus the subsidence that is due to sediment loading effects, right? And this goes back to some classic literature about how you might get at tectonic subsidence. I'm not going to spend too much time on this, right? But it's through a process that we call decompaction and backstripping, right? So you have a fully lithified section here with a bunch of different units. Those could be defined based on their formations or on individual beds. with different temporal constraints. And the first thing you're doing is essentially restoring that rock to its original thickness as sediment and density, right? That's the decompaction part. And then you're stripping that sediment load off the basement, right, through some isostatic adjustment to get at that original tectonic subsidence value, right? So that's decompaction and backstripping. That's kind of the first major step, right? So you're going to do this for step 1, unit 1 that you have here. The next step is to go up to the next layer, unit 2, and you're going to do the same thing. You're going to restore it to original thickness and density. I forgot to mention, you're going to have to do some water depth correction to kind of correct for how much it's loaded by the water mass on top. And you're going to reconstitute the unit, and then you're going to remove that subsidence from sediment loading. Now, that process over time will enable you to generate a tectonic subsidence curve based on the section or the area that you're interested in, right? That's the whole point of this. And in fact, most tectonic subsidence curves that you see are a single line that's generated from this backstripping decompaction process. But as we know from the reality is if you want to assign a single value, for instance, to say a sandstone unit, right? Sandstones have a huge range in porosities, right? And this is just a plot of a compilation of different data from different types of basins. And so there are a lot of parameters that go into this decompaction and backstripping, like surface porosity, porosity depth coefficient, the grain density, the thickness of the unit, the water depth, right? That has an uncertainty. All of these features have uncertainties. And in the past, we've just assigned single values, or even for a single formation, we've been like, well, it's sandstone dominated, we're going to just call it a sandstone for the whole formation. But what we've been trying to do as a group is develop a little bit more of a complex model that incorporates some Bayesian statistics to instead be able to couple in all the different uncertainties in these types of backstripping exercises. Okay, so this is a paper that recently came out from Tianran that goes through this kind of framework of this model. The model's open source on Julia and developed in Julia. And so what you're doing here is taking detailed stratigraphic data. It doesn't have to be one formation. You can do this bed by bed in a composite section that you design. Then you're going through the backstripping and decompaction process. But when you're doing that, all the parameters you're putting in are not just single values, they're just distributions of values. You might include other sources of error, right, associated with lithology, for instance, like say it's not just a pure limestone, but it's a sandy limestone mixed with shale. You could add some uncertainty in that. And so what you're doing is then running this through kind of a Monte Carlo simulation. So instead of getting one single value, you're getting a whole range of different possibilities for how that tectonic subsidence curve happens through time. Okay. The next step of this would be taking those thermal subsidence modifications and now adding in our age constraints of the succession, okay, based on if you're lucky enough to have some radiometric age constraints, fantastic. It might be a relative age constraint. You might use a detrital zircon max depositional age, right? If you have fossils, you can use those as relative age constraints. In the classic kind of model we've developed, you pick a position of the onset of thermal subsidence. Most people would say it's a transition from clastic dominated to carbonated dominated strata. But in more recent versions of this, we can have the model kind of pick the rift-drift transition based on the shape of the profile. And what you can generate out of that is an age depth curve with some uncertainties, right? And that's doing is saying it's creating an age depth curve that's matching a kind of Mackenzie style of thermal, like exponential decay that you'd expect from the thermal subsidence phase of a rift-related basin. So here we apply this example to Svalbard, looking at the Neo-Proterozoic of Svalbard. I'm not going to spend too much time on this. It's very far from northwestern Canada, up here in the Arctic, north of Norway. But the point up here is that there's a classic dominated package of the Veterana group that's rift-related, and then a big carbonate platform on top that's thought to record thermal subsidence. Interestingly, this is probably rift-related extension subsidence that's associated maybe in a back arc setting associated with the kind of circumradianian arc system. It's a whole other question we could talk about some other time. But what we're doing here is taking the few age constraints we have. So we're not correlating anything from chemostratigraphy, despite Svalbard recording a really robust chemostratigraphic age profile. We're just using local age constraints. We've got some DZ max depo ages, couple Riaz ages, and then the base of the Sturdian diamictite here. And then we generate a tectonic subsidence curve with some uncertainties, right? We can output an age depth model from about 800 and let's say 850 up to about 720 in this case, because we're looking at the pre-Sturtonian part of the succession. And then for any horizon in here, let's say we want to know what the base of the Svanberg-Fjellett formation is, we can generate an output that says, hey, this is the horizon. We get an age constraint plus or minus some uncertainty, right? So we've done this for the occurrence of different fossil assemblages. Now, this is a relatively simple kind of drift succession. People feel relatively comfortable with it. It gets a bit more complicated when you start to look at other margins, but this is just to show an example of an approach we could use to help understand and model how time's distributed in basins, and particularly basins that don't have a lot of age constraints. Okay, so in northwestern Canada, Raina's been working on this project. It's relatively recent. We've been going in here and starting to think about this, but we've been asking kind of three questions. What is the history of Neoproterozoic, early Paleozoic extension and passive margin sedimentation? Can we use the same approach to get better age models for the Ediacaran Cambrian transition? And how confident are we in this approach across a more complex rifted margin? So I'll talk a little bit about this. The idea here, though, and Raina's been working hard on this, and it's a lot of work, is to compile a lot of stratigraphic, biostratigraphic, and lithological data. And in this case, we're going to focus on the Mackenzie Mountains, but we've been doing this in other areas in northwestern Canada. And then we're going to try to compare and contrast other areas, which I won't have time to get into today. So we're going to go up here into the central Mackenzie Mountains. And instead of just focusing in on the Ediacaran, we're going to just look at subsidence through the entire Windermere supergroup and all the way up into the Devonian to look at how many potential rift episodes are there and how could this succession be accommodated. Okay, so within that central Mackenzie corridor, we're going to be looking at particularly the Sequi Mountain, Mount Aduni map sheets, where there's been a lot of really detailed mapping by the GSC over the years. And we have really pretty well constrained successions, some of which are published in literature, data from Shale Lake, data from Sequi Brook and June Lake. And I'm going to return to these areas later for a different reason. But the point is that you have areas that are kind of shelf, outer shelf deposits and distal slope deposits. And one of the things we were really interested in is if you're going to use this approach and backstripping decompaction just generally to understand subsidence, how confident are you in creating one section to be representative of a region, which is generally what's been happening in the past? How do we know, how comfortable are we with lateral facies changes and different positions within the kind of stretched crust to reconstruct these types of things? So when we do this activity or we do this kind of effort for Sequi Brook, okay, right here, this is kind of the tectonic subsidence profile we see, starting from about 750 down to about 400 million years old, or 490 or so. And as you can see, generally, there's a relatively steep accumulation rates that look somewhat consistent through the majority of the Neoproterozoic, and then things start to flatten out here, starting at around 500 MA. So normally one would pick, say, hey, this is around where we see the transition from rift to drift or so. And you can calculate that value based on the model. That's our T naught. We get basically an onset of rift or thermal subsidence about 504, 503 million years ago. If you compile that data across now the proximal shelf to the slope deposits, these are both slope, this is more of a shelf succession, you can see similar profiles across each location. The total amount of tectonic subsidence is different, obviously, because you have different thicknesses of units and different amounts of stretching locally. You can see all of them have some kind of structure to them. But interestingly, when you calculate the T naughts and beta factors, the stretching factors are all relatively similar, pointing to kind of similar history of the onset of thermal subsidence happening kind of in the middle to late Cambrian, or sorry, early to middle Cambrian. So that's a comparison now across different parts of the margin. If you start to think about the actual local geology and how that couples with the tectonic subsidence profiles, obviously, this shouldn't be too much of a surprise that geology should match what we see, right? So sure enough, there are these really interesting kind of inflections that you see in here and here that probably reflect local Tonian to Cryogenian basin development like we see in the rock record, right? We see the development of the Coates Lake group and the sedimentation in rift-related basins. We see the same thing through the Cryogenian. This inflection at the bottom matches the timing in which we see evidence for early Middle Cambrian extension and rifting, the opening of the Richardson Trough, as well as local volcanism, the old cabin volcanics. And then there's even a little inflection here in the Ordovician, like you want to expect from the local presence of Ordovician volcanism that's been recently kind of worked on and dated by Rosie Cobbett at the YGS. What's kind of cool is that the timing of this onset of thermal subsidence matches what David Moynihan and others had suggested as a large sub-Janshanian or Ferungian unconformity that you see all throughout northwestern Canada. All of which kind of points to a much later onset of thermal subsidence from other areas, like to the south, like people have documented further south. But more and more we've looked at areas such as Death Valley, and Tienron has a paper about this right now. We do see evidence for essentially protracted extension throughout the entire Tonian Cryogenian and into the Ediacaran potentially, and delayed onset of thermal subsidence into the early Paleozoic. That seems to be consistent up and down the margin, which is something we've been working on. Okay, so the question was, can we use our understanding of subsidence sedimentary basins to aid in our age models? Yes. I think this tool is really useful, especially in basins that don't lack a lot of age constraints, like a lot of Mesoproterozoic basins. The sensitivity analyses show that there's some consistent subsidence patterns, which is helpful. And that's even if you change across depositional settings and unit thicknesses and look at internal little facies variations. The key thing here is we can't yet do any age modeling because there is protracted extension, right? So we kind of start to violate the Mackenzie style approach of an instantaneous rift event. Now, if folks that know this literature, Jarvis and Mackenzie published some papers later that suggest, well, if rifting is short-lived, then this kind of classic Mackenzie style model still works. But you have to start thinking about the complexities of both depth-dependent extension, finite extension, how lithospheric thickness changes through time as a function of protracted extension, and how multi-phase rifting affects this. So before we're going into any age modeling, this is something we're working on right now, is thinking about how we might model multiple rift events to generate a more consistent and constrained age model through these types of more complex successions. Ideally, we want to expand this approach to other basin types like foreland basins and strike slip basins. Those add a lot of different complexities that we're thinking about. And one of the most important implications of the work we're showing right now is this subsidence work basically shows that there's polyphase extension all the way through into perhaps into the Ediacaran with a mid to late Cambrian onset of thermal subsidence. Okay. So I'll jump into chapter 2 here, vignette 2, which is about the Shuram carbon isotope excursion. So we're going to do a major pivot away from what I was just talking about and talk a little bit more about sed strat and isotopes. Don't really need to spend too much time on this. I'd say the vast majority of folks in the group know about the Shuram. It's a big negative carbon isotope excursion. It records this really sharp downturn to negative values with this gradual return to values that are more enriched, variability and very small point-to-point differences, and expression over tens to hundreds of meters of strata. And as been documented by many folks in the past and kind of summarized in this paper by James Bush, all of this kind of occurs within a marine flooding or transgressive sequence, which I'll talk about a little bit today. It's just a kind of modified map showing where people have documented the Shuram in different places, as well as a compilation of isotope data from different areas. Okay. It also is probably no surprise to folks. There's no real clear consensus on its origins. There's been a host of explanations that are primary, authogenic carbonate oxidation, dissolved organic matter, methane release, and so on. And then there's been a whole host of other explanations that reflect both diagenesis and hydrothermal alteration. Okay. What I thought I'd do today is kind of walk through what we see in Canada for folks. So the Shuram was originally recognized by Francis McDonald and folks looking at the geology from the Mackenzies all the way to the Ogilvies. And what we recognized in this work was there's a big negative carbon isotope excursion, a little bit more muted in Sequoia Brook in the southern Mackenzies. That is in the Game Trail Formation. Okay. Now this was kind of an original publication that just kind of documented it. And so what we wanted to do in James's PhD work was to dig in much more detail to this unit. So does it reflect a synchronous global carbon isotope excursion? That was kind of our first question at the time. Well, we need better age constraints, and we need to distinguish between local and global signals. Is it a primary, secondary isotopic event, or are there potential records of both? Right. So the idea was we needed these high-res data sets that are really well constrained from a sedimentological perspective. And ideally, we could look at them across these shelf slope transects. Okay. So this was James's PhD work, and we focused in on the game trail formation across the Wernecke and Mackenzie mountains. Okay. Okay. So back to our map. We were down here earlier in the central Mackenzies. We're going to return there in a little bit. We're going to head up here into the Wernecke Mountains, in particular, an area that's called the Gauze kind of Corn Creek regions. And again, we're going to focus in on the game trail formation. So I got really excited about this when I went down to work with David Moynihan in the Nataline River area, because the game trail formation in the deep water slope successions is huge. This is the whole carbonate dominated package. It has a really sharp transition from classic dominated rocks. And the underlying unit, the Nataline Formation, is full of black shales that we thought had a lot of potential for rhenium osmium geochronology. So this is kind of the initial target. As many of you are probably aware, we were able in this paper by Rooney and Canteen and others to constrain the H to actually generate rhenium osmium dates both below and above the game trail formation. So we've got dates of about 575 and 574. Here's an isochron in the upper part of the Nataline Formation beneath the game trail. And then over in the Coal Creek Inlier, we have a date of about 567. We also have a new date of about 567 over here in the Wernecke Mountains that are kind of bracketing the game trail really nicely. And as many of you might be aware, like these are consistent with ages from Oman, South China, Newfoundland. So it's an older contribution, but I thought it's just worth bringing out here as an important one, given what we see in northwestern Canada. So that was kind of step one, is to get some better age constraints, which was useful. The next step was to do some much more detailed work mapping and looking at these shelf slope transects. So this is a geologic map that James produced from a compilation and some of our own work over the years in this Gauze Creek to Corn Creek down all the way into the Nataline River area. So we're up here in the kind of east central or far eastern corner of Yukon, close to the border with Northwest Territories. And what's important about this, just to simplify it, is when you go from the Gauze Corn Creek area down into the Nataline River area, you essentially cross over what was the kind of paleo shelf slope break. Okay. And I like to think about this area like a good analog for the game trail is the Yucatan Peninsula. This is turned around looking south here, where you transition from shallow water carbonate deposits out into the slope. And the Yucatan is interesting because it also records a transition kind of from ramp to rim shelf, which is what we see in the game trail. Okay. Not going to get into this in too much detail, but James did a lot of really detailed work logging from the shelf to the slope, detailed said strat, and coupling that with carbonate carbon in black, and then calcium isotopes in the next column over that are coded based on their strontium to calcium ratios. Don't worry, I'm not going to belabor this in too much detail, but just want to show that we're kind of logging sections across this transect. Okay. Just to give you a sense of what the rocks look like, right? You go to the shelf and we're looking at rocks that are just pre-Shuram, pre-nadir of the excursion. On the shelf, what's really cool is you see the development of a really big paleokarstic unconformity right across the boundary. So right at the transition, there's evidence for subaerial exposure. You get mud crack development, paleokarst development, right before you go into the flooding surface that marks the base of the game trail. That interval in the slope is recorded by this really sharp transition into coarse classic dominated strata full of things like climbing ripples that reflect really high sed rates. That's probably the low stand wedge associated with this regional base level fall at the pre-Shuram interval. You go then up into the Shuram rocks, right? On the shelf, you get really rapid progradation and development of a beautiful kind of cyclical carbonate platform like one might expect. Evidence for things like, all kind of classic kind of mid-shelf, mid-ramp to outer ramp to inner ramp type facies, herringbone cross stratification, hummocky cross stratification. And then out on the slope, that's coupled with this big, thick carbonate dominated package with beautiful carbonate turbidites being shed probably from the platform in shallower water. So major progradation of the platform. during the Shuram. And then the top of the Shuram-bearing rocks, the top of the game trail, there's another major paleokarstic unconformity and evidence for subaerial exposure. So here is a photograph of the student standing on this contact where you see big karst development, big karst towers with pods of karst breccia that extend tens of meters down into the underlying platform. On the slope, you get this really interesting kind of thinner condensed interval at this time period that's dominated by things like debris flows with shelf-derived material, soft sediment deformation, and or condensation. So at least you have this kind of reconstruction of the margin. So James kind of put this together now and coupled it with the actual isotopic data, right? So here's a kind of a 3D model of what you see in the game trail formation. At the base of the Shuram, kind of right pre-Shuram, you get the sequence boundary with subaerial exposure and some transitional, these kind of classic dominated low stand wedge deposits. That's this breakdown here. So you go from enriched values, subaerial exposure. You get transgression, like we've documented before in the Shuram bearing rocks, progradation of the carbonate platform with beautiful deep water carbonate sedimentology associated with it. That's where you record the carbon isotope values that are at its nadir in Northwest Canada all the way down to minus 15 per mil. Okay, that slowly climb back up to 0. Above that, there's another major sequence boundary where you get subaerial exposure developed on the shelf, right? And that's this sharp transition up here where you then, during the next subsequent transgression, you return to more enriched values that you see up on the slope and the shelf. So that's the kind of record you see in northwestern Canada. And the thought was, well, do we see the same kind of progression across other margins? And as many people have documented, the question is yes, or the answer is yes. We've just slowly documented in a bit more detail. And that is that in at least these other successions that we are examining with co-authors at the time, we're looking at carbon isotopes and calcium isotopes now. A lot of these have the same kind of tripartite sequence stratigraphic framework: subaerial exposure, flooding, subaerial exposure, right? With the most depleted values being recorded kind of within the right above the basal subaerial exposure event. And consistency in kind of calcium and carbon isotope values. I'm not going to get into too much detail. So when James compiled all these data and then couple them with the paleoenvironmental information, you can look at the data here from northwestern Canada, which is in these triangles. When you look at a transition from inner ramp deposits, the shallowest water, to the slope deposits of this isochronous package of rocks, right? There's a really interesting depth gradient where the carbonates in the shallowest waters are still depleted, but they're much more enriched compared to the deeper water rocks that are much more depleted. And you can see that here really nicely, that there's essentially a water depth gradient with more depleted values in the deeper water successions. And you can reconstruct that for other margins as well, and you see that same relationship, and you see the same thing within the calcium isotopes. So the important things the takeaway from this study was, one, that the presence of the Shuram, the flooding interval, precludes some models of alteration, for instance, like subaerial exposure and meteoric diagenesis. But what this suggests is that there's likely a range of early diagenetic conditions that influence the carbonate geochemistry, with potentially, depending on how you interpret the calcium isotope data, the most well-preserved rocks recorded in the most deeper water settings. Okay. And so to bring some of that together here, Northwest Canada provides this really nice archive of the Shuram across the shelf slope transect. These coordinated shifts in depositional environments suggest eustatic change across the Shuram on the scale of tens of meters to maybe hundreds of meters as far as base level change. I think probably one of the most interesting things about northwestern Canada is the development of this karstic unconformity that is at least locally a really good base level constraint of at least tens of meters of sea level fall. So when you start to talk about that scale and the time frame, we're talking about glacial use to sea or ocean basin scale reorganization. And then from the geochemical, geochronological perspective in Canada, the data suggests that this excursion is globally synchronous between about 574 and 567. Obviously, as we if we get better constraints on that window, like that's within the relative age constraints we have now. Maybe that will fall apart when we get more high precision dates. But given the mass balance and oxidation kind of budgets or oxidative budgets, the magnitude of this change, right, may not reflect a global perturbation to marine DIC. I think more likely you're seeing some kind of amplification of a primary signal through platformal or diagenetic processes. Okay, so we'll do another little pivot here, hopefully sparking interest more from the paleo crew who's joined today. And what I thought I'd do is talk a little bit about Ediacaran, the patterns of Ediacaran fossils in northwestern Canada. So there have been many talks this fall, it looks like, on the Ediacara. I've had a heinous teaching schedule, so haven't been able to join in for many of them. But as many of you know, the Ediacara Biota are these exceptionally well-preserved soft-body fossils. They're globally distributed. Locally, where they're found, they're generally quite abundant and diverse. And these, as many of you know, these are probably some of the most clear, unambiguous macrofossils and evidence for animals in the record, and both stem and crown group animals, or sorry, metazoans. Okay, as you're probably aware as well, they've been traditionally assigned into these three evolutionary assemblages, right? Where you have the oldest Avalon assemblage, the kind of middle White Sea assemblage, and then the youngest Nama assemblage. And they're kind of taxonomically distinct, but obviously there are forms that carry through all three assemblages or in one or kind of two assemblages. So this is kind of our concept. I think this has been tested many times and it seems to be quite robust. There are still questions related to how consistent this is across different parts of the world. When you go ahead and start to assemble all this information into different types of database, this is compiled recently by Tom Bogue in this paper in geobiology, and you're looking at global diversity of Ediacara, and there's this generic diversity, right? I think that the general trends that you see are pretty consistent and have been talked about quite a lot before. So if you go back to kind of Mark Laflamme and Xuhai Zhao's paper in 2009, this initial Avalon assemblage, I think, is most simply kind of described as kind of occupation of that initial morphospace, right? And I think that makes a lot of sense to me, which is then followed by the subsequent taxonomic diversification that you see in the White Sea assemblage, right? And then there's this interesting pattern where it looks like that taxonomic diversity and generic diversity declines across the White Sea Nama assemblage that could reflect extinction, as many of you probably heard in recent talks. So if you then couple that with information on depositional setting for each of these assemblages, there's kind of this interesting pattern that sticks out, which is that the Avalon assemblage basically only is recorded in basin kind of slope deposits. So let's just say deep water, very vaguely defined, okay? In contrast, the Nama occurs across many different paleoenvironments, and the White Sea seems to also be kind of restricted to kind of shallower water environments, which is kind of an interesting relationship, right? And this was something we were really intrigued by. And we thought, hey, shelf slope transects might be able to test this. The problem with these patterns, as many of you are aware, 75% at least or greater of the total generic diversity is just represented by 4 locations, right? The kind of 4 type regions we have. The Flinders region in Australia, the Nama group in Namibia, the Conception group from the Mistaken Point in Newfoundland, and then the White Sea assemblage or White Sea area in Russia. So this geographic and temporal and paleoenvironmental isolation, it's just fundamentally problematic, as we're all aware, but it is a reality. And so any place we can get more information, especially across shelf slope transects, is really, really powerful to test some of this and to kind of dig in a little bit. So our goal in this, and this is really just an ongoing project, was to kind of get at this in 2 different ways. One is, do the Ediacara Biota really appear in deep water and then migrate to shallow water environments? That's completely opposite what we see in the Phanerozoic. Well, we would really need some well-calibrated isochronous. Obviously, isochronous is very hard to do in sedimentology and stratigraphy unless you have really, really well-constrained fossils and temporal constraints. But ideally, let's try to get as close as we can in these shelf slope transects. In an ideal scenario, you have minimal taphonomic preservational biases. We all know that's impossible, but hey, let's do our best by walking as many of these sections as possible. And then does this 3 assemblage concept start to hold up when you're looking at age equivalent successions in the shelf and the slope? So again, we need the same kind of info. So we've been focused on the Rackle group trying to couple this. I'm going to go to two different areas. We both talked about them already. We're going to go back to this Gauze Corn Creek area and the Sequoia Brook area to kind of get at these two questions separately. And this is where all the fossils have been described previously. So we're going to be looking at rocks in the Nataline Formation, which is right below the Shuram, and then rocks in the Blue Flower Formation, which is right above the Shuram. And as many of you are aware, Guy Narbonne and his students over the years have done incredible work looking at the Ediacaran fossils and successions in northwestern Canada. And what they found over the years is if you look at the Nataline Formation, right, you see a beautiful Avalon assemblage series of fauna where you have abundant discoidal organisms and then kind of rare to low diversity rangiomorphs and arboreomorphs. So this would be the pre-Shuram succession, and it definitely occurs below it, and we've documented this more in a couple other localities. Okay, now you go above the Shuram and Game Trail Formation into the Blue Flower Formation, and this particularly within the Upper Blue Flower Formation, you start to see the appearance of similar taxa like discoidal organisms and rangiomorphs and arboreomorphs, but you also start to see the appearance of different types of tubular organisms like Sequitubus here. And then Guy's also over the years described one potential Dickinsonia morph here, which is called Windermeria. Okay, now when you compile that with all the different types of morphogroups you see in the Ediacara Biota, you essentially kind of cover 3 and maybe 4 of these different groups, with a total of about 10 genera and 3 morphogroups in northwestern Canada and about 100 document kind of published specimens, although there's obviously more that people have found and haven't been published yet. Okay. And that's both from the Nataline and Blue Flower formations. So that's what we know. And so we wanted to go up into this Gauze Corn Creek area and look across these shelf slope transects to see, hey, do we see this progression of faunas from the Avalon being stuck in deep water and then progression up into shelf much later? And so the Nataline and Blue Flower make really good tests of that. Okay. So again, this is our shelf slope transect we're going to. We can look at age equivalent successions down here and up in the Gauze Creek. We can also look at stuff from Sequoia Brook and other areas in the Mackenzies. But this is just to remind you we're going across this shelf slope transect. And sure enough, when you look at this is work by Tom Bogue and James Bush and Eric Sprilling and myself. If you look at the Nataline Formation, which is our Avalon assemblage units, we can log sections from shallow water to deep. And you can do the same from the Blue Flower Formation, shallow water to deep water. Okay. And what we end up seeing here is we're trying to document kind of like from the sedimentological perspective what the setting is, but then also spend a lot of time just looking for fossils. And it's not just fossils, we're looking for the potential for fossil preservation, right? Because we could absolutely be biased in just not seeing things because there's not the right type of environment. So we're looking at not only indicators of shallow water versus deep water. These are turbidites, beautiful Bauma sequences. These are mud cracks, shallow water. But then also, do you see things like actual fossils? This is Beltonelliformis. Or do you see things like beautiful mat grounds and trace fossils, right? And what's interesting is after spending a lot of time looking at this rocks, and Tom Bogue estimated that when you combine the work we've done with all the previous work by Hans Hoffman and Guy Narbonne and other folks in this part of the world, it's probably something like 300, 350 person days on these rocks over the years looking for fossils. And what we found is that in the Nataline Formation here, sure enough, the only place we find fossils are in the deep water slope deposits. And as you go onto the shelf, we just don't find fossils. And this is despite the fact that we're looking at facies that have things like mat grounds, facies that have things where you should expect the same type of event style preservation, and we're not seeing it. In contrast, if you look at the Blue Flower Formation, which is our younger kind of white Sierra Nomala assemblage succession, there are fossils across the whole shelf slope transect. So it does look like the Nataline faunas are restricted to deep water settings while the Blue Flower faunas are depth independent. And that's a really interesting relationship. And the beauty of it is it's a very simple one to test. People can go look at pre-Shuram Ediacaran strata that's shallow water and say, oh, we found fossil, and then this whole idea is gone. But for now, at least it holds up in the shelf slope transects. Okay. If we look down at Sequoia Brook, we're doing the same thing to the south in the Mackenzie Mountains now. Okay. And this is a little bit of a kind of diversion a little bit, but I was really interested in going back here because the Shuram carbon isotope excursion in the game trail isn't really well developed, and we were kind of curious, why is that happening? So this is why we went back to Sequi Brook. But while we were there, we ended up stumbling across a lot of really cool new fossils that I thought I'd share today. And this is part of a paper that's in review from Scott Evans. But we found a lot of examples of really well preserved sequitubas. These are tubular organisms that were documented by Guy and his students recently. And we found lots of examples of these on in situ slabs with many different specimens, kind of expanding the scope of what's been described here before, which is cool. We could actually start to think about ecology on that the bed scale in certain places. And these are in situ. And I want to emphasize something that's really important here. Most of the fossils in the blue flower are from the uppermost blue flower formation, and they occur within kind of a transitional succession into the overlying risky. What we're talking about are fossil finds now that we found right in the lower blue flower formation. So I'll just return to this for a second. So right in the lower blue flower formation and right in strata that have this 567 date. So these are really, really close to the top of the Shuram. Okay, so what else did we find? In the same area, we found a really multiple beautiful examples of Olazoan. So this is another tubular organism that was recently really well documented by Rachel and Marion folks over in South Australia. This would be the first report of this fossil outside of South Australia, which is cool. And I'm just going to keep going here. We found quite a few really interesting things. We also found another example, and in fact, abundant examples of this tubular fossil, Phoenicia. This is really well documented in South Australia, likely a tubular organism. And we found many in situ slabs with tens of specimens of these organisms on it, including locally their holdfasts that you see tied to them, which is very similar to what you see in South Australia. So that's a cool new addition to the Northwest Canadian faunas. We have what probably appears to be the first example of Mossinides, which is a holdfast like disc outside of South Australia. So here's an example from Australia. Here's the Mossinides from the lower blue flower formation. It gets cooler. We also have now found the first example of Ewa Andromeda outside of South Australia. So here's some beautiful examples from Australia. This is the Northwest Canadian version. And this could be one of the first radial morphs in Laurentia, which is cool, and happy to be told I'm wrong on that. But from my read, that was kind of my impression. But there are others that I think are more exciting, right? So people will recognize this, pretty obvious, right? There are multiple examples from slabs of Dickinsonia that we found in the lower blue flower formation. So these are characteristic of the white sea assemblage, but they're also the first report of Dickinsonia in Laurentia, which is pretty cool. It would help kind of support the Windermere call that Guy made from the upper blue flower formation. We have the first report of Kimberella outside in Laurentia, which is also characteristic of the white sea assemblage, as well as the Kimbericness traces associated with Kimberella and its kind of radular traces. And then a whole bunch of other organisms that we haven't really had time to document in detail. We don't know exactly what they are necessarily, but a bunch of other forms within the succession that are characteristic of either both the White Sea and or the Nama assemblages. Okay, so cool new discoveries of faunas from this part of the world. So to revisit this was kind of our understanding of Northwest Canadian diversity, generic diversity of different morphogroups of the Ediacara biota. Between this discovery at Sequi Brook and another couple localities that we found in other areas that we haven't really published yet, we now have this type of understanding of the distribution. We've almost have the vast majority of all the different Ediacaran morphogroups within Northwest Canada now. And these new finds likely increase the total number of taxa, Ediacaran taxa, by about 5 to 10 times. So pretty exciting new stuff from this part of the world. To summarize that, the shelf slope transects currently support this offshore to onshore macroevolutionary pattern. We've got these first unambiguous occurrences of Olazoan, Andromeda, Dickinsonia, Phoenicia, Kimberella, and Mossinides in Laurentia. These communities are in the 567 or so lower blue flower formation, so they're consistent with white sea assemblage, okay? But they're about 7 million years older than the oldest reported white sea faunas, okay? So that shrinks the Avalon time window quite a lot. And they occur in unambiguous deep water settings, which would be the first report of white sea faunas in kind of this unambiguous deep water succession. So I'll just leave these questions up or these conclusions up, and I'm happy to take any questions.
Thank you so much for an excellent talk. We will now open the floor for questions. If you'd like to ask something, please use the raise hand feature and I'll call on you, or feel free to type your question into the chat and I'm happy to read it aloud. Greg, you are the first one with your hand up.
Oh, Justin, that was great. Enjoyed that very much. And I have two questions actually. Oh, I don't seem to have got my video going. There we go. The I totally agree that there's paleocasts involved with the Shuram. In particular, it's very similar in the Wernecke formation, of course, which has the anomaly, and Nick Christie Blick, among others. Chris van der Wutsch, we all think that that was really a deep paleovalley. What do you think of the idea that that paleovalley could be about 565 million years old and correspond to the Bou Azer glaciation in Morocco, and that most of the anomaly is a weathering of the valley walls, of the paleocast walls? Because you have it somewhere between 574 and 557, 557. 565 seems about right there.
Yeah, thanks, Greg. Well, I think there's a lot there to your question. I'd say that, John Husson would be the best person to ask about the Wanaka Formation and his interpretation of the development of the Paleo Canyons. I don't I don't think it makes sense to drive the excursion by meteoric diagenesis, right? And if you look at the isotope conglomerate tests, right, the excursion, the values that you see in the actual clast are already depleted, right? So the idea is that has to be recorded in the carbonate before they're eroded and weathered. Now that doesn't mean that the Paleo Canyon itself could be a 565 event if you want, that you don't want to tie to Buazer glaciation. That's totally possible, but that would have to post-date the Shuram and reflect the erosion, the base level fall and erosion. And it's possible that given the constraints that we show, that big that sequence boundary at the top of the Shuram could be equivalent in age to that same canyon filling event. We don't see from all the work we've done any kind of that significant scale Paleo Canyon development associated with that sequence boundary in northwestern Canada, for what it's worth. But there's definitely significant paleokarst development locally.
Excellent. Yes. No, I love John Husson's data, and in fact, that was one of my main arguments. But to move on, my second question is, in your title slide, you showed red beds in the blue flower, which surprised me. Now, where the fossils that you're finding now, it's not red there, but are they really red, or is it just an artifact of the view that you showed in your title slide?
Yeah, so in fact, you can kind of see it right back here. So the game trail this is a shallow water succession of the game trail. This is up in the Gauze transect. And in fact, right above the game trail formation, the lower blue flower formation in the Gauze A, Gauze B area is undoubtedly terrestrial red beds and fluvial deltaic deposits.
Oh,
there
so
are no fossils within that part of the succession. The fossils all occur right above it in what's called the disk member. If you look at kind of Leanne Pyle's work that was done here in 2004. So the fossils occur above that red bed dominated succession. Now, what's interesting is that lower blue flower kind of deltaic terrestrial non-marine package, as you trace the transect south into, you see the transition into marine dominated facies in that same interval, and those locally have fossils in them. Hope that answers your question.
Yeah, that's great. Thank you so much. I appreciate it. Yeah, what to think about.
Yeah, you're welcome.
All right, we have just a comment in the chat that says EU Andromeda is also found in the Dochanteau formation. So,
yeah, that makes sense. I think what I was trying to say is I think this is the first report in Laurentia.
Justin, great talk. I have maybe two questions, or maybe you can expand on your first part on a subsidence curve. And you kind of already mentioned this complexity, but I'm just wondering if you can say a few more about sort of what can be done with it. So first question, like you use a Mackenzie model, but like there is also a symmetrical model, but I guess more difficult to model in terms of subsidence. But it would result in very different subsidence curve on upper and lower plates. So clearly, like would have major implications for sort of how you model subsidence, and you probably thought about if it can be modeled or how it can be incorporated. And the second question, you also kind of mentioned it, but sort of you have very long thermal subsidence, and it's likely was actually episodic extension and rifting, like I think on western and eastern margin of North America recommend people recognize two periods of rifting. And so I'm wondering how it would play in a subsidence, because like if you already have extended crust and when you're extending it again, probably it will have very different effect if you sort of extend it in one go.
Yeah. Great questions, Andre. Appreciate it. So the answer, like, well, yes, we've spent a lot of time thinking about this. With respect to your first question, it's almost impossible to, like, the constraints you'd have on trying to do depth-dependent extension and model that are they're so broad that it's very hard to know like what your mantle stretching factor would have been in a scenario like this. You can look at the modern, you can constrain yourself based on modern margins and use those values to help inform your model. What we've generally found is, ultimately the only thing you're actually going to be able to do with some confidence is to kind of just imagine the simple upper crustal part of the extension process. And that's still, like, even if you had a huge mantle stretching factor, that would just kind of reduce the amount of that crustal stretching. And you'd still see a similar form of rift related to thermal subsidence within the upper plate or in the upper crust in that part. And so you can still use that simple Mackenzie style model to understand at least what's happening locally, right? With respect to protracted extension, there's a lot of things to think about with there. So if you look at the kind of Jarvis Mackenzie literature and other folks afterwards, right? If extension lasts longer than about 20 million years, like an individual rift event lasts longer than that, then you start to have to think about using kind of a non-instantaneous framework. And there's a modeling framework we can use to do that. But if you imagine that these rift events, they're kind of short-lived rift events, and they have thermal subsidence, kind of components of them, one possibility is to think about ways to stack multiple events together in a smart framework that links them together that still does the same thing. What you need to do is, like you're talking about, change probably the lithospheric thickness across each of those, right? Because if you extend the crust once, now your crustal column is thinner, and there's a thermal anomaly you're going to have to deal with and let that decay away, and then you're going to have to do it again. And so the modeling gets much more complex in these systems. What you can do is isolate the parts that you're interested in. Like, say, okay, there's Kryptonian cryogenic extension. Well, I can't use this age model to understand anything within that interval, but I could use this age model to understand the terminal rift event and the thermal decay associated with that. And all I need to do is think about how that lithospheric thickness might be affected and the thermal kind of component of that. So the way I've been trying to kind of mention this is, like, I think it's a tool in the toolbox, right, with respect to this. And especially if you're like in a mesoproterozoic basin where you have one radiometric age constraint and it's an intercratonic sag basin, which most of our records come from, this could be really useful to just give you a broad sense of, like, hey, like, I'm at this horizon, it's 1540 plus or minus 20 million years. That's better than nothing, right? And that's where I think this is actually probably quite useful. Hope that helps.
Thank you. I'll ask one more, but maybe I'll let Daryl go first.
Sure. Hey, Daryl.
Okay, well, first of all, it was a great job, Justin. Like
Thanks.
to see more of that. Can you see any difference in the net subsidence or the subsidence rates between the north end of the Mackenzies and the south end of the Mackenzies?
Oh, that's a great question. We've gotten caught up in trying to understand how to deal with the protracted polyphase rifting. So we've been really focused on that part of the central Mackenzies just because the data is so rich there that we feel really comfortable doing these little sensitivity analyses. I will say that the plan is to go from the Ogilvies all the way down to the southern Mackenzies and then connected in the southern Cordillera. And I can say that the hardest part in being able to assess that is challenges we've had with some of the lithostratigraphic correlations amongst things like the backbone ranges, right? Which actually includes rocks that are as old as Ediacaran and as young as Cambrian along strike. So our first step is we really need to kind of clarify that. That's something I've been working on with Rob McNaughton and Karen Vallis at the GSC. And then we can kind of do a better job and I'd feel more comfortable. But as like just from the way I would think about it from that is, yes, there's absolutely a change that you'd expect to see along strike in the Mackenzies. And the problem is that we're not also kind of thinking about how we might model the effects of the work that you've done documenting the kind of late Mackenzie Mountain supergroup and how like the Little Doll and so on, which I think would affect the kind of initial crustal structure, especially when you see like how much Little Doll there is to the north versus the south. So that's something that I really want us to dig into as well.
That's great.
But yeah, it's a really good question.
The second question before Andre takes all your time up.
Yeah.
The thing that fascinates me about the interval you're looking at is that you've got some large olistoliths in it.
Mm.
Are they related to drop in sea level? Can they be related to those unconformities, or do you think they're just coincidental margin collapse?
Such a good question. Yeah. So in particular, within the kind of Twitch-Akil transition, right? Twitch of Mount Profit, and then also within the Nataline Formation, we see intervals dominated by huge liths, some of which are like, building scale and also are not all, well, it's interesting. So some of those match the platform geometry and composition nearby, and they look locally derived. And I've always thought that's like, as far as like the Keel Twitcha Profit Twitcha package, that's probably oversteepening of the margin with collapse of the carbonate platform into the basin. But there are intervals where we're seeing outsized class from underlying basement lithologies. And that's a really interesting one. because I think you either have reworking of some of the cryogenian tillites and that are up section we've seen in a couple areas, which would be really kind of a cool story that would be fun to talk about sometime. But the other option is that you're actually exhuming older basement rocks and depositing those during kind of a local rift event in the Ediacaran. And so I think there's a couple spots where you could document kind of syn-nataline extensional faults that could be responsible for sourcing older lithologies. And we see a little bit of an inflection in this tectonic subsidence curve in that interval too, matches the timing of rifting you see in the southern Cordillera. So that's also a possibility that I think is going to be worth pursuing.
Okay, well, I hope you carry on with this work. Looks good.
Thanks, appreciate it.
We got a hand raise from Mark.
Hey, Justin. Can you guys hear me? Yep.
Yeah. Hey, Mark.
Perfect. Thanks so much. Awesome talk, as always. Really, really appreciate this stuff.
Yeah,
I was kind of wondering about your team's sense is, do you guys still think that these kind of three assemblages are real, or is it just a signal that's driven by an absence of data from key locations, and this will kind of all appease itself, or it's just not a temporal signal, it's another kind of signal or something?
Yeah. I guess I won't speak for like Scott or Eric. I can just speak for myself. I think that there's probably a true signal there. I think that our records right now are just too fragmented and isolated to really dig in enough to see it and to be really confident. What's interesting is there's definitely some overlap in faunas that we know should happen that we just haven't really clarified yet. But there does seem to be right now a compositional difference between the lower blue flower and the upper blue flower that kind of match maybe a white Xenoma assemblage with some overlap. I think to me, what's interesting, at least, is there's probably quite a bit of time missing in the middle of the blue flower that we haven't really appreciated, which makes sense with kind of Greg's question of the red dead package. Like there's a lot more time in that, and that also makes sense with the ages, right? Because most people, if you look at the upper blue flower, it transitions gradationally into the risky, and most people think the risky is right at the Precambrian-Cambrian boundary, and the bottom of the blue flower is 567. So all of a sudden you have a lot of time in that one unit. And so I think that probably is going to help at least locally separating those parts of the blue flower out into those two assemblages. But I do really worry about the kind of spatial network or spatial kind of constraints we have right now on these three assemblages. And I think the more we can do on successions that record, isochronous packages, same age strata, and really compare and contrast, the better we're going to actually tease that apart.
That's brilliant. Thanks so much.
Yeah, thanks.
Quick comment from Ron Raybird is, yep, we need to apply this methodology to the sequence B sections, compare the 15-mile, Hematite Creek, MMSG, and the Shaler, and then we can go to Prescott, who has her hand up.
Hi, Justin.
Hey,
I was
Prescott.
curious, do you guys have any redox data through the blue flower yet, or is that work that will be done? And how does that compare to our understanding of where these organisms might have been living?
Yeah, I mean, fortunately, Eric Sperling's 2016 paper, there's really detailed redox data through the whole blue flower package, right? And it's in the form of iron speciation data. I think there could be a lot more work that could be done on some of the carbonate proxies as well, which is something that Kim Lau, as part of our collaboration, has been working on. But the signal, like you see in many places, a bit heterogeneous, right? Like on an iron speciation kind of proxy, like locally, a lot of these rocks are anoxic, right? But they're full of fossils. And so something that, Eric Sperling would be a better person to kind of ask his thoughts on that. But yeah, we do have data. It does, with shifting the end Shuram date to 567, there's actually quite a window of time in here in the White Sea time where we actually don't have a lot of data. And so I feel like there's a lot more that we could do to explore that.
Cool, thanks.
Yeah.
Andre, did you have one more question?
Yeah, so I just wanted to clarify, so I think you mentioned that when you found Beltanella formis in what was it, Nadalina formation?
No, it's the Beltanella formis is only in the blue flower formation.
Okay, so on a shelf in Nadalina you didn't find nothing.
Yeah.
But
yeah, the only thing we find in the Nataline is consistent with all of Guinard bones, which are rangiomorphs, arboriomorphs, and a bunch of different types of discoidal organisms.
But in a slope environment.
And only in slope settings. We've scoured the shallow water settings. You've got the microbial mat textures and you got the preservation potential there. We just don't find stuff. Now, maybe we're not looking close enough. Maybe we're not looking at small enough stuff. I feel like there's a lot more we could do there.
And this Beltanella formis you found in lower part of blue flower or upper part? Is it close to 567 or?
Oh yeah, most of the Beltanella formis we found is in the upper blue flower.
Okay.
Yeah, not in the lower blue flower.
Okay. And I guess you don't have exact age constraint for upper blue flower, right?
We don't. Like, my hope was we could use the subsidence, modeling approach to provide a better age model for heights throughout the succession. But we really need to do a better job of figuring out how we're going to model the polyphase kind of component. Like, we can put it in a standard Bayesian age model and I could give you some sense, but I feel like we could probably do a little bit better. So that's something we're working on right now. But I will say, we've spent Alan Rooney has spent a lot of time, we've tried to run a lot of blue flower rocks over the years and really struggled to get any dates from anything in the upper blue flower, which is surprising because there's beautiful black shales, but they just have no rhenium in them, which has been sad.
Okay, thank you. Great talk. And
Thanks,
we
Andre.
had a really big crowd today.
No, that's great. Well, it was my pleasure, and I'm sorry, but I have to split right now. It's 12:15, so
Yep.
good to see you all. Thanks for the invitation.
Thank you very
Okay.
much.